when a random process passes through a LTI system. Then you have multiple random processes, one at the input, one at the output, how they are related to one another, what is the uh, relationship of their autocorrelation functions. After that, we learned about the famous Linear Khinchin theorem, which says that and the Fourier transform of the autocorrelation of a random process gives us an idea, gives us a power spectral density, or in other words, it gives us an idea of what is the amount of power present for different frequencies that are present in the signal. So it gives us the power of the various frequencies present in the signal if we take the Fourier of the autocorrelation. And we saw this example. This example is also very simple. We have already seen that autocorrelation of a random process, which is just a random variable, was 1/3 in the last lecture, if you could just remember. We saw autocorrelation of a uniform random variable, which was just a random process. It comes out to be 1/3. And then if I want, the autocorrelation is found 1/3, then what will be its power spectral density or PSD? It will be just the Fourier of the autocorrelation will be just 1/3 delta F. Cyclostationary process, as I told you, is not in the course. So now we have found the power spectral density, which is power per hertz. Okay? For any frequency, you will get the value of power per hertz once you find the power spectral density. Now, if I want to find the total power, very simple, just sum or just integrate over all the PSDs of your spectrum. You just sum up over all the power spectral densities. So it is power per hertz. You are summing over hertz, you will get the total power. All right. This is one formula. Another formula that is used will be that we know, yes, that autocorrelation is the inverse Fourier. If power spectral density is the Fourier of autocorrelation, then we know that autocorrelation is the inverse Fourier of power spectral density. Now, if in this formula, if I put tau is equal to 0, you can very well see that the sum of the power spectral densities is also equal to the autocorrelation function at 0 delay. So now you have two formulas to find the total power. One is that you sum the power spectral density over all the frequencies, you will get the power, or you can just find the autocorrelation at 0. Tau is equal to 0. This will be for White-Stein stationary process. Remember that we are talking about these stationary or WSS process because as you could see that this theorem was defined for stationary random processes. So, stationary is White-Stein stationary. We are all talking about White-Stein stationary processes. So you have this very important property. Autocorrelation 0 gives us the total power. So applying to the same example. So this was the power spectral density in the last example we saw earlier. Just PDF of the autocorrelation, which was cosine, and you got these EJs. EJs had these impulses. Now I just want to find the total power. So I will just integrate them. Alright, so it will come out to be two sums, two integrals, and delta will this will be constants will come out. Delta integral is 1. So a square over 4 2 times this becomes the total power. You can also find the total power by this formula. You had the autocorrelation, just put tau is equal to 0, you will get the total power. Now, how can I find the power in LTI systems? Meaning that if I have a random process with a mean and autocorrelation as an input to a LTI system, so we know that output is also a random process which is given by the certain properties that we learned earlier. So the properties were that the output's mean will be equal to the input mean times the sum of the impulse response of the LTI. This was proven. Then we saw that the autocorrelation of the output will be equal to the autocorrelation of the input time convolved with the impulse response, and again convolved with the impulse response, but with tau flipped or with the impulse response flipped around the tau axis. And we also, the cross correlation between x and y will be the autocorrelation of x convolved with the flipped version of the impulse response. Now I will just take and try to write them in terms of their Fourier spectra. This is very easy. You can very well see that this is the impulse, sum of the impulse response, and sum of impulse response always corresponds to h0. All right. So h0. What is h0? H0 means frequency response at DC frequency, h of f. H of f is actually h of t into e minus j 2 pi f t. So h of f is the Fourier of h of t. But if I put f0, then ejf is totally ej0, so this becomes 1. So impulse response, sum of is always equal to the DC value of the spectrum h of 0. All right. So I can just write this as h of 0. So I've written this in terms of the Fourier response. So output mean is the Fourier of the impulse response at 0 frequency or DC times the mean of the input. Now this you can take its Fourier. This this will become power spectral density of x. This will become h of f. Now what will be this thing? So h of minus t. So h of t is h of f. We know that h of minus t is equal to h of minus f. And if I take conjugate of h of minus t conjugate, so once you take conjugate, you have to take conjugate on this side as well as the frequency is flipped. So it will become conjugate of f. All right. So and then we also know that h of t, it is a simple impulse response of a real system, so it is real. So h of conjugate of minus t is equal to just h of minus t. So I can write that h of minus t is has a Fourier transform of h of conjugate of f. All right. Another thing, you can also go from here. From this, you can also see. All right, h of minus t, h of minus f. But we know again that h of t is a real impulse. The impulse response is real. It is just a simple LTI system on the real domain. So we know that its Fourier will be conjugate symmetric. So you can just write h of minus 1 f is equal to h of conjugate of f. So h of minus t is h of conjugate of f for under these conditions. So this means that h of minus t will be h of f conjugate. This is h of f into h of f. This becomes h of f mod square. While this will be just rx tau, product convolution becomes product in Fourier in frequency domain. So this becomes s of x product with you have h of f conjugate, as we saw. H of minus t is h of f conjugate. These are all the Fourier formulas, and this explains the formula. So the first formula means that mean value depends on the response of h of f at f0 at the DC, which I also explained. And you can see a second equation that the output autocorrelation is equal to input times the h of mod square. So you can see the power only depends on the mod square of h of f. For example, if h of f is a differentiator, so its mod square will be its square mod will be 2 pi f. Square will be 4 pi square f square. So you will just multiply the input PSD with this mod square, and you will get the output PSD. Also, we saw that the cross correlation is Fourier of the cross correlation, and we saw the cross correlation was r of x convolved with h of minus of tau, and so its Fourier will become s of x into h conjugate of f. You can also derive another formula that will be x sy of x. So we have seen earlier that ry x tau is equal to rxy minus tau. Okay, this we have seen, because if you say this is t1 minus t2, then you have flipped, so this will be definitely t2 minus t1, so this will be minus tau. All right, this we have seen earlier. So what is Fourier of syx of f, right? Syx of f, Fourier of this will be syx of f, and Fourier of this, some steps sometimes are missing in the book. You can always see my notes. So we know now that r y of x of tau is equal to r x y of minus tau. All right. So I take the Fourier, then I will have syx of f. I just take the Fourier. So tau becomes f, s, and this r becomes, from the Linear theorem. This becomes sy of x. This will become sx of y. This will be minus f, minus tau minus f. All right. Then you can say that r xy of minus tau. This r xy of minus tau. Okay. This will be sxy of minus f. All right. Then I can say that r xy of minus tau can also be written as sxy f conjugate, because again we know that this cross correlation is between two real numbers, between two random processes. All right, there e of x and e of y, the cross correlation of two random processes, okay, which are real. So this will be real. So because of this reality, we know that these Fourier transform will be conjugate symmetric. You can just write rxy of tau as sxy conjugate f. So this can be written as sxy conjugate of f because of conjugate symmetry. So syx of f can be written as sxy conjugate of f. So sy of x comes out to be equal to sxy conjugate, and we have just found this. So just take its conjugate. This will become, this is already told you, this is just power spectrum. This is just positive value, so its conjugate will remain real. It is a real number, while this could be conjugate, this could be complex, and hence you take its conjugate. This becomes a conjugate. Conjugation cancels. Right. This gives an idea. This could be complex, but sx and sy, they are generally real and non-negative only because they represent the power. Right. By cross correlation can be complex solutions. Simple example. So hf is this. So I want to find the output PSD. The process is the same cost which was giving us this PSD. So I just take the product of the PSD with the mod square of HFF, and I will get the output. If I want to find the cross correlation, so in the cross correlation I have to take HFF conjugate. So HFF for our differentiator is 2 pi f j2 pi f into this. So because it is conjugate, it will be minus j2 pi f into s of x. S of x is the same, the PSD of the auto operation of the cosine, difference cosine, which we saw in previous examples. So this will be minus j and this will be plus. There are two mistakes here which you can correct. Just take the product of with the PSD of the cosine, which we did earlier. So mistake, this will be plus and this will be minus, and the results will be so if I take this example was again the random process, which was uniform random variable, and we saw its PSD. The its autocorrelation was 1/3, so its PSD was 1/3 delta f. So if I want to find its if I pass this through a differentiator, then what will be the output PSD? Output PSD will be again mod square of the differentiator times this. But once you take this, delta f only exists at f is equal to 0, and f is equal to 0, this is 0, this will be 0. Similarly, the cross, it was conjugate, so this will be conjugate, but again it only exists at 0, f is equal to 0, but at 0 this is 0, so the output will be 0. Many times you have these sum processes. For example, signal is added with a noise, just for a sake of simplicity. In that case, we have did already an example that for this sum process, the autocorrelation comes out to be autocorrelation of x, autocorrelation of y, autocorrelation of xy, and autocorrelation of yx, as we saw earlier, the last lecture. So if I just take its Fourier, this becomes s of x, this becomes s of y, this becomes s of xy, this becomes s of yx, s of yx. But we saw s of yx, okay, it can be written as s of xy. S of yx is equal to s of xy. So you can write this as s of xy. This is s of xy. This is also s of, but this is conjugate. So a number with its conjugate means you will just get the real part 2 times. So you can also write it like this. So this gives an example that the power spectrum density of some process is the sum of the power spectra of the individual processes x and y plus a third term, which is actually depending on the cross correlation or the Fourier of the cross correlation between the two random processes. And an important example is that if I say that x and y are uncorrelated, then you know that the autocorrelation, which is actually E of xy, will become E of x separate, E of y separate. So it will become mean times mean of y. And if say one mean is 0, that is the mean of any one of them is 0, then we know that rxy will be definitely 0, because any mean is 0, the whole will be 0. If rxy is 0, then you definitely know that s of xy will be 0, because s of xy is Fourier of r of xy. If the signal is 0, what will be the Fourier? The Fourier will also be 0. This will be only totally 0. Hence, the PSD for some process, provided the individual processes which are being summed are uncorrelated, in that case, the PSD of the sum process is equal to the just equal to the sum of the individual PSDs. So another simple example, here the sum process was equal to x of t, and x of t is again the same cosine function t1 minus t2 that we saw earlier, and we found its PSD and all that. And then same process goes to a differentiator. We have seen also this in the previous example. All right, and we found the output y of this process. We also found the cross correlation between x and y. All right, so whatever y was this total, so we have found the cross correlation. इसमें मेरे ख्याल से इससे गलती हो गई, क्रॉस कोरिलेशन यहाँ प्लस होना चाहिए था, यहाँ माइनस होना चाहिए था, शायद मैंने नोट्स में किया भी हो, ठीक है ना, ये था, ये इसकी ऑटो कोरिलेशन थी, ऑटो कोरिलेशन का आपने ये फोरियर लिया था, इस फोरियर को फिर आपने अपने डिफरेंशिएटर से पास किया, जब आपने पास किया तो जो क्रॉस कोरिलेशन थी वहाँ पे तो J2 pi f का you got its conjugate. Alright, so this was the cross correlation, ठीक है, between the input and the output. Input was x and output was d by dt xt. So that input correlation, its Fourier will be this thing, but you can see the Fourier में जो गलतियाँ वो आप नोट से ठीक कर लें, but you can see the Fourier is a j, so its real will be 0. So if its real is 0, then you can say real is 0. And if this means that they are uncorrelated, the autocorrelation is 0, or you can see that the autocorrelation is not 0, but you can see that they will cancel. All right, the real part is 0. This means that the sum process PSD will be just equal to the individual sums of the individual processes. All right. So this again, you can I think switch to the notes. 7 steps are missing. So you can see this is 0. So this will be just PSD of x, which we saw, it was just a cosine function and all that. X of y of f, which was actually s of x times hf mod square. So this is your s of x. You just autocorrelation of the cosine thing, or the PSD of the cosine, and this is the PSD of the cosine times with the mod square of the differentiator. All right, so you can see these two are common, you can take them outside. A square, all right, 1/4, because here this will become 4, j will cancel, mod Because of mod, this will become 4 pi f square. So 4 will also cancel. You will just have pi square f square. Alright, so this will be the answer as shown here also. The next thing is Gaussian and white processes. So Gaussian processes, they are very important in communication. And the fundamental reason is that the thermal noise in every electronic device, which is actually produced by the random movement of electrons due to the thermal agitation, can be modeled by a Gaussian process. Thermal noise is a Gaussian process. Why? Because in free electrons, all right, you've also seen this electromagnetics that their motion is quite random. Even if you apply electric field, there is still random, just a little bit shift. So free electrons, because of thermal agitation, their movement is quite random, could be in any direction. All right. So their velocity is a function of and the velocity is higher the temperature. We have seen the higher the velocity of the electrons, the more kinetic energy. Now these electrons, they will produce a current, we know, and every electron will produce a current, and every current will be random value because they could have random motion, so they will produce a random current. So each electron produces a tiny current. The current is a random variable because you are mapping the random movement to a real space in terms of the current. So current becomes a random variable. Could be positive or negative depending on the direction of the movement of the electron. Or in one direction it could be positive, another direction could be negative, as we have seen for currents. The total current generated by all the electrons, which is the thermal noise, the sum of the currents of all these current sources. And we can see that most of them are independent. Every electron is moving independently. This we also saw in electromagnetics. So the total current is actually the sum of large number of independent identical currents, identical distributed random variables. All right, and we know that once we have these central limit theorem applying, adding all these but of IIDs, independent identically random variables, we always get a cosine. Very important theorem. You have said, I think you have. Haji, क्या नाम है इनका? Salman sir, have you studied the central limit theorem in your previous course? पता नहीं कौन से स्टूडेंट्स हैं. हाँ, Salman sir, can you hear me?
जी सर.
Have you studied the central limit theorem in your previous course?
Central limit theorem, जी सर पढ़ा था.
Thank you. All right, thank you. So this you can see it is being applied. So we can very well model thermal noise as a Gaussian random process. If you will sample the process at any time, fix the time, you will get a Gaussian random variable. All right, so a formal definition, based on formula, definition of Gaussian process is in order now. So if I say I will get Gaussian random processes and I sample it at all these times. So the important property is that we know all these random variables will be Gaussian. That is well-known fact. But another thing is that they should have a jointly Gaussian density function. अच्छा, क्या नाम है इनका? Salman sir, have you studied a jointly Gaussian distribution function?
सर ये ना उसमें सर ऐसे ने बस एंड में बताया था कि जॉइंट वो जो एक गॉसियन रैंडम प्रोसेस वो है जिसकी जो डिस्ट्रीब्यूशन फंक्शन है वो जॉइंटली गॉसियन है, लेकिन इसकी डिटेल नहीं पढ़ी थी. गॉसियन रैंडम वेरिएबल पढ़ा हुआ है लेकिन ये ज्यादा डिटेल में नहीं पढ़ा हमने. ये जॉइंटली गॉसियन रैंडम डिस्ट्रीब्यूशन ये नहीं पढ़ी हुई.
So we will go through this right now. It is a little bit different. It is Gaussian, but it has additional property. That is why it is called jointly. So I think we should just go through it right now. So, all right, this is actually the exact formal definition is that for two random variables to be Gaussian, jointly Gaussian. We also call them binormal or two normal random variables. So they must have a joint distribution of this form. All right, where this rho is the correlation coefficient, So if this is of the form, then they are called binomial, or you can say that they are jointly distribution. And it can be shown then that each x and y, we know they are normal. All right, no, this is already true. Okay, but you could just have taken their product. Okay, will they be jointly distribution? They can be, provided they have this, they satisfy this definition. Okay, so if they satisfy this definition, so each of them is normal random variable. So here we are just talking about joint distribution of two random variables, not about a process. Process will come later. So yes, each of them is normal random variable, but as well as the conditional distributions as given y and y, they are also Gaussian. So this gives us the difference between joint Gaussian random variables and two random variables that each have a Gaussian distribution. And this joint random variable definition can be, or jointly Gaussian, this can be extended to more than two random variables. If I say 3, all right, then for any given one of them, the two must be jointly Gaussian. All right, and you will also have definition for the 3, how they will be, the 2 can be extended also a 3 joint distribution. All right, so the main property is that if you have n random variables which are jointly Gaussian, then any subset of them is also jointly Gaussian. Okay, and individually they are also random Gaussian random variable. They are completely characterized by their m's and by their. Are you, any question? They are completely characterized by their m's and by their p's, which we just I told you, by their m's and p's, or your rows, you can say row. They are completely characterized. The whole function is totally defined, and you can also any linear combination. If you just take any sum, let's say sum, any linear combinations of some of those or all the random variables. Okay, then you can see that the output will also be jointly Gaussian, because we have already said that you can take any set and it is jointly Gaussian. Okay, so any linear combination will also give us a jointly Gaussian random variable. Now any linear combination of these, you can get many random variables, they will also be jointly Gaussian, Gaussian, as well as those linear combinations, the new random variables that come from the linear combinations of these random variables. For example, I say x1 plus xn, x1 plus x2 plus xn, whatever combination I can make, but it has to be a linear combination. So you can see that the linear combination will be random variable and they will also be jointly Gaussian. And if we have uncorrelated Gaussian random variables, then we have already seen if we have uncorrelated, then it is also independent. It is only and only true for a Gaussian random variable. So independence and uncorrelatedness are equivalent for jointly Gaussian random variables, but is not true for other random variables. So definition has now been can be understood now. So if there is a Gaussian process, then at any time each random variable, if you sample the process, yes, it will be a Gaussian random variable, but we can see that all the random variables, they will be jointly Gaussian. This means they will have all these random variables have a joint Gaussian distribution, as we saw earlier just before, a jointly Gaussian distribution of several random variables. Same thing, any instant random variable is Gaussian, and at any 2 points random variables are distributed on a two-dimensional jointly Gaussian distribution. This example, so we have a zero mean stationary Gaussian random process. Mean is 0. PSD is given. You can see this is a box from minus 5,000 to plus 5,000. Height is 5. He says what is the PDF of the random variable x3. So I sample this process at 3. What is its PDF? So I know PDF, you need to have the mean and you need to find the variance. If you have these things, you can find the PDF of the random variable. All right. So it is already given that the mean is 0. All right. If the mean of the whole process is 0, then you can see that the individual mean will also be 0, because first of all, the mean is constant. So whatever the mean of the process will be the mean of the random variable. All right. So you can see the mean is 0. So of the process, if the process is 0, and you can say at any time the mean is 0. This means at time 3, definitely the mean will be 0. Next, we want to find the variance. So variance is sigma square is equal to x minus eta whole square. Eta is the mean is 0. It will be just e of x square. But what is x square? X square is x of 3 into x of 3. Random variable x of 3 into x of 3, which is actually what? This is Rx of 0, or autocorrelation at 0. This autocorrelation function with no difference, it will become autocorrelation at 0. You can, and we know that autocorrelation at 0 gives us the power, total power in the PSD. So you can just take this function and find the power. What is the power? 5 multiplied by 1000. 5000 watts is the power here. All right. This becomes the variance, and so variance is found, mean is found, and hence you get the PDF of your random variable. So here we saw that one random process is jointly is Gaussian process if each one are random variables, as well as any set has a joint Gaussian density. Here we are saying that two random processes, when they will be jointly Gaussian, if you take times into sample times, you sample your functions x and y. Now this total is a joint Gaussian distribution. In that case, it will be jointly Gaussian. If they are jointly Gaussian, then each of them will be individually Gaussian. Very true. So properties of Gaussian and jointly Gaussian random process is as given here. So if a signal is passed to an LTI, output will be a Gaussian process. All right, and as well as X and YT will be input and output will be jointly Gaussian. So you can see very easily because we have seen that linear combinations of jointly Gaussian are themselves jointly. So if you are passing through an LTI, so what will be LTI will be just like it is convolution. It's taking product and it is just taking adding, just doing linear combinations. So if you take linear combination of a random process of any random variable, the output is also the same random variable. If it is Gaussian, it will be also Gaussian. If it was jointly, the output will be jointly. So linear combinations are also jointly Gaussian. So this means y of t and x of t will be jointly Gaussian. So this also gives a very important property that if the input is Gaussian, then you very well know that the output has to be linear combination of the input. All right. So for non-Gaussian process, it becomes difficult because input statistical knowledge will not give output simply. But for here, you just know if the input is Gaussian process, then the output will also be a Gaussian process. Again, we saw for Gaussian joint Gaussian was uncorrelated and independent. This we saw also earlier for Gaussian random variable. The same boils down to a Gaussian process. So again we say we have the example, and it is passed to a differentiator. So this example I think was all right. So this is a previous example where you just saw that this example, this example. So you have this PSD, all right, but he says now this PSD is passed through a differentiator, all right. So what is the output PDF of the random variable as the same sample time, but now that PDF is passed to differentiator, you get a new output, and then you sample the output at 3. So you want what is the PDF. So we know differentiation is an LTI property, all right. So output will also be jointly Gaussian random variable as was xt. So xt PSD is given, and we know also the xt was 0 mean, and we have also find its variance, all right. Now first of all I will take the PSD of x of t, which is already given, and I will multiply this with the PSD of d by dt. So then I will get the PSD of the y of t. From the PSD I can calculate the variance, but how can I calculate the mean of the output? So we know the mean of the output was given by this formula, that. So we know differentiation Fourier is this, and output mean is equal to input means times the sum of the impulse response and some of the impulse response we have already seen can be found out by taking the DC value of the spectrum, which gives us some of the response. So we know DC value, it is J2 pi f. At DC value this will be definitely f0. So your h will come out to be 0. H will come out to be definitely 0. So mean is 0. So we have found the mean. Now we want to find the variance. Okay? For variance, what we can do? First of all, the output spectral energy is the input times the HF mod square of the differentiator. All right. So variance mean is 0. So again variance is E of y square. Y square. Let us say it was working at y3 slot. It could be any different slot. So it could be y of 3 into y of 3, alright, because mean is 0. So what is y of 3? This is actually for a station was becomes out to ry 3 minus 3 or iy of 0. Again same thing. It is just the sum of the PDF. Alright, but what is the PDF? PDF is actually the input multiplied by 4 pi square f square, and the input was at height 5. So you multiply, this becomes 5 into 4 pi, all this f becomes f cube over 3, and the height goes from, this becomes f cube over 3. This is a constant, everything is constant. This is f squared. This becomes f cube. Put the limits for 500 to minus 500. and this will become minus again minus plus 2 times f1 square. Hence your variance comes out to be this value. This value, and hence your random variable comes out to be this value. The last part of this chapter is the white process. So what is the white process? White process derives its name from white noise. From white light. Light is white. All right. Why we call light as white? Because it consists of all the frequencies. All right. So white process is a process which consists of all the frequencies and their height is constant. So white process, formal definition, white process, it is a flat power spectral. Its spectral density is a DC, straight for all frequency, DC in DC spectrum, straight line. All right. And fact is that the thermal noise, which we just studied, which is a Gaussian random process, its PSD is a white process. All right. Now problem is that if it is a white process, then from infinity to infinity, the power will become infinity. But actually, it's not so simple. It is not same height for all frequencies. It is actually given by this formula. We don't have to go into detail of this formula. So, but overall, actually, you can write this height as kt over 2. All right. So you can just put the so as you increase f, this will be tending towards 0. All right, because this factor is increasing, this will be tending towards 0, but this is very slow up till this frequency 10 to the power 12, which is up till the limit of most of our communication stuff except optical fiber. The drop in SN is almost 90%, but is almost only 10% value is decreased. So we can almost say that for our practical purposes, our thermal noise can be modeled as a white process of height n naught by 2. So n naught is equal to kt, and hence you can get your all right. So this will be from now on height is n over 2, n naught over 2, and it will extend. So we normally say kt is equal to n naught. So if height is kt over 2, we will say that it is n naught by 2, and now we call the PSD of the white process, and which we know it is also the thermal noise. So for Fourier, if spectrum is 1, time dependent is del of t. So if it is n naught by 2, so its Fourier inverse will be n naught by 2 delta tau, because tau's Fourier was n naught over 2 DC spectrum. All right. This gives that the autocorrelation is this thing. This means that if tau is 0, if you have no difference between t1 minus t2, then you will get n naught by 2. Otherwise, you can very well see that for any other tau which is not 0, which is non-zero, you would always get a 0 value. This means that the random variables are independent, as well as they are here they are uncorrelated, but you can also show all right. So we have thermal noise, which is white, but we also know it is Gaussian. All right. So it is not independent, it is uncorrelated, and the properties are as follows. Thermal noise is a stationary process, it is zero mean process, it is a Gaussian process, it is a white process, and all that. Now, many times what happens that this white process is passed through a filter. Okay. So filter, it has a certain bandwidth. You just get the process around a certain bandwidth. So we have studied in 2.7 also that they become band pass signal. Normally your signals AM and FM, they are centered around FCs. So if they will go, if those they are centered around FC, and then they go through a certain electronics which passes this it is a band pass filter, as we just saw in AM and FM radio applications. So you have a band pass filter, it passes the frequencies around FC. So the noise will also be passed around FC. So noise will also be a band pass process. Okay. As signal has in phase and quadrature components, noise will also have an in phase and quadrature process. Let us see an example. Let us say we have two filters. One filter is like this. Let us say a double sideband. You can see very like double sideband, and this is single sideband. All right, only the upper sideband is there. There are these two filters. They are of height 1. So here, even if you take the square of 1, this will be just 1. Now input is a process, and not by 2. I multiply this with filter response, which is 1. Definitely the output will be n not by 2. But this output will only exist around FC. For double band, this will be around FC positive, negative, both greater and higher. For single, it will be just from FC to FC plus W. This will be 2W, this will be W. So, and we can represent our XT again as, the in phase and the quadrature components. The low pass, in terms of low pass signals, you can also represent it like this, as we saw in. There you're representing signals. Similarly, you can also represent noise, because noise is also passing, is also a signal, and it is also passing through the same filters. And some of the properties of filtered noise, having the in phase and the quadrature, is that they are also they are low pass. Yes, they are not band pass. They are the low pass version of your band pass signal, and they are also jointly stationary. They are also jointly Gaussian random process, and all that. Uh, the power is same in the actual or in the cosine or the in phase component, as well as in the quadrature component. So you can see the PSD of the real the cosine